Let's talk about the Elasticity Lab. You took your springs and you applied a weight and you measured the stretch. Knowing the original length and the stretch, you could calculate the strain. You measured the diameter of the spring, divided it by 2, and you got the radius. So you could calculate the cross-sectional area. Well, from the weight and the area, you could calculate the stress, and then you can graph stress over strain. Of course, 0, 0 has to be on the graph because if you don't pull on it, it's not going to stretch. And you graph your data points, and we saw that it was linear. And you calculated the slope of the best fit line, which was the Young's modulus. And that's the stiffness of the material. The Young's modulus represents the stiffness of the material, not just this object. If it was wider or longer, we're taking that into account. So we're only looking at the material itself. If this was a spring constant, then we'd be looking at just that object. It wouldn't be applicable to another situation. Now remember, we're using a spring as a model. I would like to be able to use solid wire, but it's very hard to stretch. But if we had a wire, it would look like this. The diagram would be labeled the same way. Now we want to think of what the wire is made of. It'll appear to be a vertical column of atoms. The atoms are held together in bonds. You can imagine that there's going to be many columns of these atoms all lined up. Let's just take a look at one column. As we pull on this wire, each one of these bonds is going to stretch a little bit. All of those little changes in length are adding up to give us the change in the length of the wire. Well, now we're talking about stretching a bond. Well, we talked about that before with this graph. The net force turned out to look like this. That's the equilibrium bond length. And there it is on the diagram. Does this graph have anything to do with this graph? This one looks linear. That's quite the curve. Well, how about you just take a look at this portion of the graph? Flip it upside down. You get this graph. This graph is simply a macroscopic view of this microscopic view of the atoms that we can't see. So scientists use the macroscopic experiment to infer what's happening on the microscopic scale between the atoms that we can't see. This graph is linear for a small section. If we keep on pulling on here, what do you think is going to happen to this graph? Well, let's see. If we keep on pulling on this idea, we're going to find that the curve starts to level off. Well, that means this is going to start to level off too. So what's Hooke's law? Stress is proportional to strain. That's the idea of this linear relationship. So what happens if we keep on pulling on the wire? We're eventually going to break it. And we're going to have to break across all of these bonds. Well, let's take a look at this model. We only have to break one bond, no matter how long the chain is. Perhaps you've heard a chain is only as strong as its weakest link. And this gives rise to tensile strength, which is the force required to break this wire divided by the cross-sectional area. So the length of the wire will not affect how hard we have to pull to break it. So think of Young's modulus as to the stretch of the material and the tensile strength as to how strong that material is. We better practice a problem before we go any further. Now I'm going to make up data just to try a problem and not do the data from the lab. That's the data you're supposed to collect yourself. I'm going to imagine that we have an original length of 15 centimeters and a radius of 0.4 centimeters. And imagine we pull with 2 newtons and it stretches 3.75 centimeters. Let's calculate the stress. It's the force per area. Pi r squared and you get the area. There's your force. We get 3.98. And what are the units? Just get them from the formula. Newtons per centimeter squared. We're going to get the strain. Change in length over the original length. And we get 0.25. What are the units? Well, look at that. It's a distance divided by a distance. No units. You can think of this as a percentage if you multiply it by 100. In this lab, this data tells us that the wire stretched 25% of its original length with that amount of force. Now we're supposed to make a graph of stress over strain. 0, 0. But this is only one data point. I need to do this lab again and again and keep stretching it further and further and getting this new stress and strain. So here I have some more fake data, and I'm numbering the axis. I draw on a best fit line. So I've numbered the axes, draw the best fit line. We have a couple of points above and below, and we're going to find the slope of that line to get the Young's modulus. It's simply the stress over the strain read off the graph, not using the actual data points, using the slope of the best fit line. And that gives me 12 newtons per centimeter squared over 0.75, which is 16 newtons per centimeter squared. Well, what about the tensile strength? Well, we're really not working with a wire. We're working with springs, and I told you not to overstretch them. So you certainly can't pull on them until they break. So we're not going to do it with that, but we are going to do it with the rubber band. So here's the rubber band, the original length, and the cross-sectional area is going to be the width times the thickness. We do the lab all over again with the rubber band. We pull on it, we measure the change in length, and because it's a rubber band, you can stretch the heck out of it. At first, the data may appear linear. Then it seems to curve a little bit, and then it starts curving the other way. Now, that's a little more complicated than just stretching a wire. On a microscopic scale, our model for the metal is just the atoms all in a line. As we pull, we stretch the bonds. Rubber is a more complex material. We're going to use a simple model where we just have the atoms arranged in like a zigzag pattern. When you pull on this chain, you're going to find that you're going to start to open up these bond angles. So the rubber is very stretchy because we're not stretching the bond, we're changing this bond angle, if you will. And so we have a certain slope to this graph. And then after a while, as things start to elongate, the model starts to look more like this. And we end up stretching the length of the distances between these atoms. Hence, we have a more complicated graph. You can actually feel this if you just start pulling on the rubber band. It's easy to stretch. And as you get to the limit, oh my goodness, it gets much, much harder. Now in science, we use models. This is a very simplistic model of what's going on. Because it's a rubber band, you can keep on pulling this until you break the bond. That might put you somewhere up here. And we call this stress the tensile strength. Tensile strength is a special stress. It's the stress at which the material snaps. So let's make up a problem on finding the tensile strength of rubber using this rubber band. We had the original length of 15 centimeters and an area of 0.5 centimeters. But you're going to find when you do this in lab that you have to stretch it an awful lot before it breaks. It might actually stretch like 45 centimeters before it breaks. And it's going to require a lot more force than you might think. I'm putting down 10 newtons here, but it could be bigger than that. Now we know stress is force per area, but this is a special force. That's the force at which it breaks. So we'll call this tensile strength. 10 newtons divided by 0.5 centimeters squared, and we get 20 newtons per centimeter squared. Now you might think that's the tensile strength just for this rubber band. It's for rubber itself. So that if I change the geometry of this rubber band, I'll be able to calculate how strong it will be. So imagine I had another rubber band with a cross-sectional area of 2.5 centimeters squared. Would you be able to calculate the maximum force it can hold? Well, you're still going to use the same tensile strength because that's the value we found for rubber. And then using force per area, we have the new area. So we just multiply and we get 50 newtons. Hey, I think that makes sense. It's 5 times the force that we broke this rubber band with. Well, take a look at the cross-sectional area. This is 5 times the cross-sectional area of this one, which means we have to break 5 times as many bonds. Well, I think we'll be able to see the usefulness of Young's modulus and tensile strength with an engineering design problem. Imagine you have a walkway and it's being suspended by steel cables. The original length of each cable is supposed to be 3 meters. Each cable has to support 1,000 newtons by this design. When people walk across it, these cables cannot stretch more than 1 centimeter. Now that's because we can't have this thing wobbling all over the place. So you as an engineer has to decide what diameter steel cable we should buy. First, we're going to look at the tensile strength. This type of data would be supplied by the manufacturer. The tensile strength is equal to force per area. We have to support a load of 1,000 newtons, so we can calculate the area. This gives us 2.08 times 10 to the negative 6 meters squared. But how do we get diameter? The area is pi r squared. We get 8.14 times 10 to the minus 4th meters. Multiply the radius by 2, and we have the equivalent of 0.163 centimeter diameter wire. Now you might say, great, now we know what cable to buy. Except there's another condition. We can't have it stretched too much. Well, that means we have to look at stress over strain. Steel wire is about 2 times 10 to the 11th newtons per meter squared. Well, what's the strain? It's the change in length over the original length. And that gives us 3.33 times 10 to the minus 3 with no units. And if we know what the strain is, and we know what the Young's modulus is, now we can calculate the stress. And that gives us 6.67 times 10 to the 8th newtons per meter squared. That's the most stress we can put on this without exceeding the stretch. So how do I calculate the diameter? We know stress is force per area. We know we have to hold 1,000 newtons. That's the area. And we have the stress. Well, here we have the radius. Multiplying by 2 and converting to centimeters, we have a very small number. 3 times 10 to the minus 4th centimeters versus 0.163 centimeters. Well, what's the difference between these two? Well, this one is based on the limiting factor of the stretch. This is based on the limiting factor of the strength. We can't have it break. So which one would you go in order? You gotta order the thicker one. Because if you order the thinner one, it might work for stretch, but it's gonna break under that load. Now in reality, no one's going to push it to that limit. You're going to double it or triple it, or maybe even make it bigger by a factor of 10 to make sure it's not gonna break on you. When you actually build something, you have to use bolts and squeeze and put pressure on the cable, and that's going to weaken it. Well, hopefully some of these problems and what we've talked about here will help you do the lab sheet on this Elasticity Lab.